I will more talk about the techniques, methodologies, because this is school. I want to concentrate on some of the techniques. And here it's about wide resonance spectroscopies. They're not necessarily all limited to the case of wide resonance spectroscopies, and they are not limited to the case of, for example, liquid water. We can do the same in solids. So that we can apply the same methods in solids. We can apply them also. I saw them in the work package, titles of the work package. It was lots about confined systems. All these methods basically work also in the confined systems. The only limitation, what I'm using here, is that it must be a system which is non-metallic. So there must be a band gap in the system. Otherwise, this should all work. And I use liquid water because that's the case I have been studying. And of course, in the spirit of the school, I've seen there are many, many talks about liquid water. So I will use this as the example. There are some other examples, but most of the results I will show are on liquid water. And if I have time, I will then review more of our recent results on spectroscopy and liquid water. Sorry, the change of slides. Okay, thank you. So this is about, about the wide spectroscopy. It's not about liquid water only, but the approach is the molecular dynamics. I will review some of the aspects, like I said, we did just before, about molecular dynamics, about the density functional theory, because these are the workhorses that we are using. And then the question is why water? Well, you of course have already the answer in all these applications in biological systems. We are basically always covering the DNA, for example, in liquid water. What is interesting and still fascinating about liquid water, it has been, of course, studied for ages and ages with different methods, but there are still some interesting aspects which are not fully understood. And the basic block of liquid water is, of course, one water molecule. Here, one central water molecule. It consists only of three atoms, two atom types. And it is known that, well, the oxygen being more electronegative, it pulls some electron clouds from the hydrogens attached to the molecule. And thus there's a dipole moment within the molecule. And that's basically the main driving force in the condensation of liquid water. Of course, ice below the melting temperature, the electrostatic interaction between the water molecules. So this is the basic block for the liquid water. And then in general, we have these hydrogen bonds. So we have two donated hydrogen bonds, so to the nearest neighbors, two, and then two accepted hydrogen bonds from the nearest neighbors. These are for the motif also in ice, the crystalline ice. So these are about liquid water. Then these are some early results. Let's say these very early results. This is relatively new results about spectroscopic wide resonance spectroscopy of water. There are many, many examples, of course, many experiments. Yeah, I just want to show the low frequency parts of the spectrum. So this is the frequency scale. Here it's the normal, at least for me, normal scale. So the zero is here, zero frequency, and then the frequency goes up. So at low frequencies, there is two very characteristic peaks in the Raman spectrum. Also, they have been discussed and they are explained recently. So how they are related to the motion of water molecules in the liquid water. And then what has been studied is the temperature dependence of the density of those peaks. There's some shift also in the frequency, but it's more about the density of the second peak. And this is the same thing, the Raman spectra, two kinds of Raman spectra, you come to that as a function of temperature. And this is now this is a heavy water, but this is deuterated water. So instead of having two hydrogens, we had two deuteriums. So chemically, it's exactly the same. Just the mass of the hydrogens is now the mass of deuterium. And this also leads to some reduction of the quantum effects, nuclear quantum effects on the protons, changing to deuterium. So that's why the frequency scale is not the typical around 3,500 to 4,000 wave numbers, but it's a little bit lower. But this is the OD, so oxygen deuterium stretching frequency range. And then these now spectroscopists often they use the inverted scale, so the higher frequencies on the left, just to note you, and the lower frequencies on the right. These are what you sometimes see in the spectroscopy papers. So there are two panels. I can quickly do this later in my lecture. It's about different signals that we measure in the Raman spectra. I don't know how it's done in experimentally, but basically this is so-called isotropic one, and this is the anisotropic signal that one measures in the Raman experiment. So they are, you see, in the same frequency scale, but the absolute scale doesn't matter. But you see that the frequency scale is the same, but the effects are different frequencies. So with these two different methods, one can measure different effects. And then, yes, this is about the temperature dependence. So here the highest curve on this side, it's the highest temperature, and then the lines go down. So here the lowest curve is the same one. So this is the 90 degrees Celsius curve. So this is what happens in the OD vibrational spectrum region in liquid water as a function of temperature. This is experimental. And then the question is, so what happens in the structure of liquid water? So there were some early interpretation here. So they tried to model with Gaussian intensities each of these peaks. So what is the underlying dynamics in this hydrogen bond network, which constitutes the main structure of structure motif in the liquid water as well as in the iron, in the ice. Now our task is trying to explain this to the experimentalists. So we try to find the methods where we can directly simulate the signal. This is the goal of my lecture. To show you two examples, well, actually three, 2.5, let's put it that way. So I will try to introduce two basic methods, then a third, a bit more specialized one, which can be used to measure the vibrational spectra in experiments, and then computationally how we do it, how we can calculate basically exactly the same signal as in the experiments. So this is the goal of this lecture. I forgot to mention, if there are any questions, because this is also a lecture, any question at any time, please feel free to interrupt me. So again, we try to better understand the properties. We try to explain to our experimental colleagues what they maybe measure in the simulations. And then we use the atomic simulations, molecular dynamics, and we include the signal. So I will then now explain then how we get this the intensity of this spectroscopy signal. And of course, we are trying to do it fast and accurately. So I will quickly review the basics. I start from the very basics. So we use both classical molecular dynamics and then electron structure based molecular dynamics method. So what we do so far, we use classical dynamics, so the Newton dynamics, like I told before, but how we get the forces. One way of get the forces in the molecular dynamics is the density functional theory. So this is an electron structure method. If you don't know, then so this was introduced by Walter Kohn. First, the paper was with Pierre Orenberg, Walter Kohn in 1964. The next year, they published 1965, the famous Kohn-Sham equations. These are the equations that we are solving numerically in the supercomputers, starting from laptops to clusters to supercomputers, because these are the very heavy methods still today. So it's an expensive method, but it's supposed to be accurate because we are really solving the electron structure. So we get all the effects of polarization as a function of the neighborhood of the molecules and so on. And I must show this because actually this DFT was derived while Pierre Weber and Ecole were both at the Ecole Normale Supérieure in Paris, the Department of Physics. So this was the foundation. The method became more popular then little by little in the 70s, 80s, and nowadays, as I said, it's pretty basically the working method for most of the simulations that we are doing in, let's say, physics in the molecular dynamics. If we are not using the classical force fields, then I will quickly mention something on machine learning toward the end of my lecture. But then there will, of course, be much more on Saturday about machine learning. So I will stick to this density function-based molecular dynamics for myself. So the idea is we solve the electron structure explicitly. So we don't use some model for the electron structure. We solve the electron structure. It would be the same as solving the Schrödinger's equation for these many particles, all the atoms, all the electrons in the system. But we know it scales so badly, we can do it only up to some few particles, few atoms. So that's why we are using density function theory, where the basic quantity, as the name says, density is the electron density. And it was shown in this paper that we can get all the basic, all the properties of the ground states using the density as the central variable. And we don't need any mechanical wave functions. In the Kohn-Sham method, we use the single particle electronic wave functions as the basis, like in the Hartree-Fock methods. We can derive the equation. The main problem that we have still today is that we don't know the correlation term or the expression, analytic expression for the correlation term. Exchange we know, but we are led to use always approximations. And this was also, Sergei showed some examples. B-tree leap is very popular among the chemists. So we are forced to use some approximation here. And this is the main approximation that we have. The other one, the nuclear quantum effect, we have methods like path integrals, which we can overcome. But the main problem here is the missing analytic formulation of the exchange correlation, and we use approximation. Then molecular dynamics, I mean, Sergei already mentioned this, so I think I can go very quickly. So what we want is the position of the atoms as a function of time. So we want to see how the atoms move in our system, and we use the Newton's equation of motion, as said, and as shown already by Sergei, so I don't know, need to go into that. So the examples that we have for how to derive forces, that the classical force fields parametrized, that they are fixed before the simulations, or we can directly, like using DFT, we can directly get the forces along the dynamics. And nowadays, what is getting more and more popular is this machine learning. And this is in between. So we try to get the accuracy of the reference method, often DFT, but at speeds which is closer to the classical force fields. We are in between in both, but I think that's a very good compromise in many cases. There are, of course, cases where this is difficult to machine learning, but in the case, no, it's getting more and more popular, and it's becoming more and more easy to find these machine learning approximations. So there's the propagation of the Newton's equation of motion, which was also derived by Sergei. And then the question, the time step, just considering that if we have oscillations of the atoms in our system, we had to be shorter by a factor of, let's say, 6 to 10, so that we can use the propagation accurately. And typically we are left with, let's say, 0.5 femtoseconds, sometimes even smaller, 0.25 femtoseconds as the time step in our molecular dynamic simulation. And then when Sergei says 100 picosecond in the early simulation was short, our first simulations in the world of electron structure-based molecular dynamics was just maybe picoseconds, few picoseconds. Now we can go with some supercomputers. We often can go 2 tens, hundreds of picoseconds, but it's still way beyond what is needed in any of these cases of, let's say, complex biological systems. So this is also something that we cannot parallelize. So it's all sequential. You saw that the equation of motion, when you discretize them, you really have to go one time step by time step to get to the next time step. So there's no way to parallelize that. In Monte Carlo, it's somewhat different. You can do parallelize Monte Carlo, but here we are really forced to do one by one these time steps. And so they are time consuming. And we want to have every time step as fast as possible evaluation. Then that was the. So then I mentioned DFT-based molecular dynamics. It's also called, it's a general term is ab initio molecular dynamics or first principle molecular dynamics. It's the Latin saying. So the idea was indeed that we use electron structure method at this time step the dynamics. So I use usually DFT-based molecular dynamics. So we use DFT to give the forces. And this method was initiated by the method of Roberto Carr and Michele Parinello in 1985. It was popularized in a very short time, so it became possible to do molecular dynamics using electron structure methods. It was, of course, very heavy. The computers at that time, they were big, huge supercomputers, but as I said, we could do very, very short simulations. Nowadays, we seldom use the Carr-Parin method itself. We are using the so-called Bohr-Oppenheim molecular dynamics. This is just the basic idea is that we do like classical molecular dynamics. And at each time step, we do the DFT self-consistently, some convergence criterion, and then we evaluate the forces. We move the atoms using these equations of motion, and then again, we do DFT self-consistent. So this is how this DFT-based ab initio molecular dynamics works.
But it may be not with DFT.
Yeah, there are other methods, and that's why the more general one is ab initio. So, question is DFT really ab initio? This is why I use DFT based. I mean, DFT is exact, but because we don't know the function, we need to use an approximation. Then in quantum chemistry, there are methods which are also approximative, but you can improve the accuracy systematically. So there are some simulations using MP2, but again, that's even more heavy computationally than DFT, and the simulations are very short. Now the middle way is machine learned potential, so they fit the potential to usually even coupled cluster, but then they assume that they can do coupled cluster accurate molecular dynamics. But again, there's the step of the machine learning potential in between. It's really ab initio molecular dynamics because we are kind of parameterizing the interaction in between. But indeed, there are some works that it's so heavy that the DFT is mainly used here. Oh, yeah, I mean, stuck. Yeah. Yeah. Okay, so before I come to real spectroscopies, I just mentioned that the first way to analyze the vibration in these atomic molecular systems is the so-called power spectrum. So it's basically just fluid transforming the velocity autocorrelation function. And if you have a harmonic system, so the atoms got some single bonds. So it's if the system is harmonic, then when you do the Fourier transform, of course, you get the signal peak. And this peak, if you are at low temperature, and again, if the system is harmonic, this corresponds to the normal mode frequency, if you're familiar with that. So this is a static way of calculating the vibrations in the system. We get calculate the normal modes by diagonalizing the Hessian, And if the system is harmonic, indeed, this gives you a peak at that same frequency. That's just a simple consequence of the this method. But there's no correspondence to any of the experimental signal. But there's no spectroscopy which measures this directly. So now the question is, how do we generalize this to something where we can directly compare with the experiments? And the first example is infrared spectroscopy. I don't know if any one of you of that are familiar with this method. So this is about the absorption of light. We shine the sample with infrared light, and part of that absorbs. So often what is shown is indeed the absorption. So this is now the transmission. So the absorption is basically this inverted. Taking if we normalize this maximum to 1, we take 1 minus this, and we get the absorbance. So here one measures how much light is transmitted through the sample, and the rest is absorbed by the sample. And so these peaks correspond then to the vibrations in the system. And then you see that there are peaks at different height. So this is the intensity of each absorption. It could be that there are just more. For example, this is now example is the vanillin in carbon tetrachloride solution. So it's a solvated molecule. It's molecule in liquid. So it could be that there's several characteristic frequencies which vibrate at the given frequency, and that gives a high intensity, but usually this is not the case. There are so-called selection rules, and now I will come to explain how we can computationally evaluate these intensities of these peaks. And again, you see that here spectroscopically, this example high frequency sensor here. So, and this corresponds, if you're familiar, this usually corresponds to OH frequencies, the highest frequencies. So there's an OH group here. And then the lower ones, they are more collective vibrations in the system. So if you have this, then how do you learn to know what is behind this? So the first example was to calculate the normal modes, but if we want to also include this intensity in the calculation, so we start with so-called dipole approximation. So this dipole approximation is often used for the absorption of light. How do we then proceed with this? So we use the Fermi's golden rule for the calculation of the probability of absorption. So if you are familiar with the Fermi's golden rule, so we have this potential, and we have an initial wave function of the system, and all the final states. So here we sum all the final states, and then these transitions happen when there's a correspondence between the energy difference in the final state for each of the final states and each of these. So once we evaluate these matrix elements, we get the probability for the absorption at the given frequency. And in the dipole approximation, what we have is this perturbing potential is the dipole moments, and then the electric field. So if you have this electric field shining on your system, then it couples with the dipole in the system. And if the frequencies of the lights matches that of the dipole, you start to get the absorption. And this is what we see in the case of infrared spectroscopy. So we have these transitions at the frequencies of the vibration. So this gives the basic how we work with the intensities. So the intensity is proportional to the dipole. We have that in the potential, and it could be a permanent dipole or it could be instantaneous dipole. But we need to have a change in the dipole during the dynamics that we have an intensity. So this gives us some selection rules. So again, in the early case here, we didn't have any choice. All the vibrations in the system give signal. Here we see that there are different intensities, and that intensity depends on how strongly the dipole couples with the lights at the different frequencies, this infrared light which comes in. So the standard way, I have mentioned a couple of times, is to calculate the normal modes using the harmonic approximation. And many of these quantum chemistry codes, they can calculate you this. And then they calculate also the change in the dipole along each normal mode. Then it gives a number. This is the intensity of the infrared absorption. And that's based on the approximation, the dipole approximation. So how much does the dipole change along each of these normal modes? Now our task is to use the molecular dynamics to do the same. So instead of using harmonic approximation, we try to be more realistic, also because in the case of liquid, we are always out of the any harmonic approximation because the atoms are moving. So with this harmonic approximation is always usually it implies that you have relaxed the system to ground state. That this method called instantaneous normal modes, but mainly this is done at the ground states geometry. But here we are always on motion. So what we want is to have the probability of absorption, and then to see the correspondence with the experiments. And then there's a technical issue in the molecular systems. This is easy. There's some issues with the dipole moment. If you know in periodic systems, the dipole moment is not well defined. Yeah. There's been lots of discussion, and the solution to this, in our case, condensed matter simulations came about 20 years ago. We used the method, so-called method of periphase. So we can get to the dipole moments in periodic systems using these methods, and this is implemented at least in a couple of molecular dynamics codes, which do the function-based molecular dynamics. So what do we do in practice? So we have to have some way of evaluating the dipole moments, and in this case, it's still the dipole moment, the whole system. I will come later to the molecular dipoles, but it's the dipole moment, the whole system. And there are, of course, methods people have tried to parameterize this also, so that if you have a specific configuration, the classical force field gives you the forces on the system, and then there are methods or attempts to parameterize also the dipole moment in the system. And usually it's based on molecular dipole moment and how it changes in the different environments. But we have to have some methods. Now in the DFT-based molecular dynamics, the code that I'm most using, CP2K, is as one option, and it just costs basically no time, no computation time compared to the solution of the self-consistent concern equations. And we get the dipole moment along the molecular dynamics trajectory. So it's no costs, we get the dipole moment. So what do we do with this to get to the infrared intensity? Is that we take again an autocorrelation function. Earlier we did this with the velocities, the velocity autocorrelation. Here we take the total dipole moment of the system, and then this is the dipole. Here it's a 3-dimensional, because we have a 3-dimensional system, molecular system. So it's a vector product. So we take some initial time, t is equal to 0, and then how it evolves, the dipole moment evolves as a function of time. And like before, we just Fourier transform this. And then there's the so-called quantum correction, which I mentioned we are using classical nuclei. People have shown, so what would be the correction to if we were treating the nuclei also quantum mechanical. So there's a correction that people have derived, which basically leads to multiplication by the frequency, the intensity which we get obtained from the autocorrelation function, and the Fourier transform, it's multiplied by the frequency. And then it has been shown by Mark Tuckerman and others that instead of using the instantaneous dipole, we can as well because of the properties of the Fourier transform. And the time derivative, we can actually use the time derivative of the dipole moment instead of the dipole moment itself. And this leads to much faster convergence. The spectra are much smoother using this method, and we get rid of the low frequency modes. It converges much faster at the low frequencies also. And then instead of just taking the initial point of the simulation, what we do in practice is that we take several time zeros. So then we start the correlation at the difference time, and we calculate the autocorrelation, and then we take the sum or the average of these autocorrelation functions and we Fourier transform. And finally, what we get is this spectrum, and then, well, there's still a numerical trick, because if the simulation is not long enough, or if it's quite small, the system, it might be that this correlation doesn't go to zero at infinite time. This is what we usually have, for example, liquid water. From the initial configuration, if the simulation is long enough, at the end, there's no correlation with the initial dipole, especially if we use this several times zeros of time, zeros. So this should go to zero. Sometimes it doesn't go, as said, if the simulation is too short or the system is not very big, like it's always the case in the DFT-based molecular dynamics, because we can do maybe now hundreds of atoms, but not the thousands, at least not easily, or millions of atoms. So what we do is a kind of mathematical trick that we smoothly bring the autocorrelation function to zero, and this way the Fourier transform then is smoothened, and then the spectra are smoother. So this is now, sorry for the resolution. I just took one example of calculating different spectra, and I said if I have time toward the end, I will show some of our examples. So the red curve here, this is some organic molecule that has been simulated, and they compare the experiment. So the orange bars, this is the harmonic analysis. Well, let's say the DFT, so it's a static calculation and the normal modes. So one more or less gets peaks, where one has peaks in the red experimental spectrum. And then when we do ab initio molecular dynamics, well, the resemblance is usually better, but it's not perfect. There are issues because the exchange correlation is one issue, as I mentioned. Then the second one is that indeed we neglect the nuclear quantum effects. And then the third one is always the case of sampling if our trajectory is long enough. But this is basically what we receive or obtain at the end. We get these spectra, which we can compare with the experiment. And as I said, I will hopefully have some time to show some more examples later in the presentation. Are there any questions at this point?
Yes.
Yeah.
You have the spectra from DFT. This is the spectra that you calculated without dynamics.
Yeah.
And after that, you use ab initio molecular dynamics with DFT, and you have this black line, and the spectra changes. We get closer to a real system.
Yes.
In fact, the frequency shift is rather big. So we look at, for instance, 300 centimeters minus 1.
Yeah.
Yeah, so this big shifts for about 50 centimeters minus 1.
Yeah. And I mean, the main reason usually is the anharmonicity. So again, well, this one I'm a bit surprised, because usually the anharmonicity brings the frequencies down, because the shape of the real interaction potential, usually the anharmonicity brings the frequencies down. There are some cases where the frequencies go up, but indeed, and then this of course also depends on the temperature. You go to higher temperature, the more anharmonic is your system, then the shifts are even larger. But again, this is much more realistic, because we are now treating the system really dynamically, and I believe this
I mean that the frequency shift can be really essential. So 550 centimeters minus 1 would be 100 it's possible. So if you have some DFT spectra, and compare this spectrum with experiment. So we have
Yeah. And this system is quite complicated. So indeed, I can imagine that there are large shifts. So that's why we want to go with these kind of methods that we can make these more realistic comparisons. Any other questions at this point? Because this was the basics. This is what now I will repeat for the Raman. It's more or less the same story. I will go it faster. So I hope everyone more or less got the basics here. So we calculate the dipole moment as a function of time along the simulation. I mean, it's also possible that you calculate the trajectory and then later you just take snapshots, quite frequent snapshots, and then you evaluate these quantities. But as I said in CB2K, for example, it's much faster to calculate everything on the fly. Yeah.
But this said over time, the last line. It's averaging over initial time, different initial time. This brackets.
Yeah. This one. Yeah.
But you have also averaging over ensemble. No. When you calculate the moment.
Yeah.
This is whole system.
Yes, and this is whole system.
This whole system.
So it's averaged over ensemble, and then you make a second averaging over initial time.
Yes.
Okay.
Yeah. Any other questions? Yeah.
So I wanted to ask about this first derivative we start. So initially you use this correlation, you find this correlation between dipole moments without derivative, and after that with derivative, and this is also the same intensity.
Yeah. So it was shown in the paper. What was the papers by Takam and others that indeed you can use the same, but this converge is faster to the long infinite limit trajectories. So it's the property of I think Fourier transform, and you can change because of Fourier transform. You can change the time, and it gives the same result. So these are people using this. Sorry.
Second derivative.
Yeah.
Can we use second derivative?
This I don't know. I didn't check the derivation. I will.
In principle, it is possible. I mean, it will be also density, and we can.
Whether it's the same intensity, one should check, but might be. Time derivative remains the same as here. So. Any other questions, comments? If not, then again, I repeat the same. Also, the sense of time. So I come to the Raman spectra. So what happens? Well, what happened in the case of infrared spectrum was that we shine the system. Well, if I show this, we shine the system with light at a different wavelength of the light, or different frequency of the light, and then we find this transmission, or we take 1 minus this, we get how much light was absorbed. Now the effect of Raman, of course, got the Nobel Prize for this effect, comes from it's shifts from the original vibrational state to another state using. I mean, I haven't seen any real physical derivation. Want to make a derivation, but what we call is virtual first virtual excitation and excitation, and this is kind of a virtual state, whatever that means. But this is a scattering phenomenon. So there's first a relay scattering where there's no energy absorbed or emitted. So it's you return to the same states after the scattering. Now you can have the Stokes scattering, where when you first excite, the vibrational state, its virtual state, and then you drop to a different frequency, which is higher. So then you have a difference in the energy, which is proportional to the frequency difference between these two. And then the opposite is that if we start from a higher excited vibrational state, we have the virtual excitation, and when we drop here, so again we have the same energy difference. Now there's a emission of a phonon in this case. So here the difference of energy levels is due to absorption of energy due to excitation of phonon or phonon vibration in the system, and this is then the opposite. So here we absorb, here we emit the vibration quantum or phonon in the case of the solids, familiar the phonon. So this frequency difference is basically the same as before. It's a frequency difference in the vibrational states. So this effect can then be used to obtain the spectrum again as a function of frequency. And when we have the difference corresponds to the difference of these vibrant states, then we have this scattering phenomenon. And then this can be measured experimentally. And then when we calculate this, now instead of the dipole moment, we use the electron polarizability, which is the second derivative of the total energy with respect if you have the two electric fields in the system. And then just first I mentioned the selection rule. So in the first case, you had to have a dipole vibrating at the given frequency so that there would be infrared signal. Here it's the same, that the polarizability has to resonate with that vibrational motion, this difference in the vibrational frequency. So there has to be a change in polarizability at the frequency corresponding this energy difference between the two levels. And then one can show that if one looks at the character table, the harmonic analysis and symmetry analysis, there's a high symmetry of the system. So the modes in the character table, which have a quadratic form, square and so on, they are Raman active. And then there's also, you saw that this level, sorry, this is not the change in dipole, this is the vibrational state. So we go always to the next state, upper state, or one down. But there's no signal if we have the Rayleigh scattering. And then I mentioned this isotropic and anisotropic one. Then if we have this is, for example, liquid, because we don't have any direction like X, Y, Z. If you have an oriented crystal, you can have also then the polarizabilities and Raman spectra along different crystal directions. Again, water is isotropic, so we have isotropic and anisotropic signal. But if you have oriented crystal and it turns isotropic, you can have different signals in the different Raman scattering experiments. These are often seen. Again, because I use liquid water, I only use these two, isotropic one, and then we have this other signal, which is called anisotropic. And again, the procedure to calculate the intensity is the same. We use now the polarizability instead of dipole in the molecular dynamics. During the molecular dynamics, now the DFT, when we use DFT, I mentioned the polarizability is second derivative of the energy with respect to two electric fields. The first one you can calculate without any efforts, but the second effect of the second electric field, you need to take that in account, and we have to use Bayesian theory. So we don't only do self-consistent DFT, but we have to do the so-called density function of the Bayesian theory. And I don't know if any one of you of that is familiar. It's this is the same thing as what is done in, for example, codes like quantum espresso, calculate the phonon spectra, or we need it's also implemented, I think, in BUST now. So we do the perturbation theory to calculate the vibrations. And this leads to another set of self-consistent equations. So the perturbation. So first we have to calculate the ground state. It's a self-consistent Gronsheim set of equations. And the density factor perturbation theory adds to that. And usually each time step costs now 3 to 5 times more. I mentioned the dipole you get just for free, basically. But here this is much more tedious, and that's probably also why these calculus are much less frequent, because again we need long simulations, and each simulation now costs almost 5 times more. So what we do now, we calculate the polarizability, and I should mention here, I go very quickly over that. Now the polarizability, if you are familiar with that, it's a tensor. The 3-dimensional system is a 3x3 tensor. The dipole was 3-dimensional vector. The alpha is a tensor. That's, again, it's a derivative if there are 2 electric fields, and the 2 electric fields can have 2 different directions. So it's a 3x3 tensor. And then in principle, we do the same. Now it's just, if we are calculating the so-called isotropic spectrum, so we first calculate the trace of the alpha, and then the trace is just a number. So this is not a vector product or tensor product in that case. That gives the isotropic signal. So we take the trace before calculating this product. Again, it's a normal product. It's a scalar times scalar in that case. That gives the isotropic one, and then the anisotropic one, which I mentioned. So we take the tensor, we subtract the trace, and what remains is then the anisotropic part. Then we do a tensor product. So we get second intensity. This is how we get the 2 different signals intensities. Isotropic one when we use the trace here, and then the anisotropic one when we use the anisotropic part, so the full polarization minus the trace. That leaves us with orthogonal anisotropic form. And again, we can use the same tricks as before. So I go here very quickly because it's basically the same thing, just replacing dipole, except the tensor. So again, same things. We have the several time zeros, and then ensemble error, which is on. So, and we arrive just here to a very, very simple example. Well, this was some Jupyter notebook example. So we came to this, but I hope I will have the time to show the real simulation in the liquid water. What I also show, yeah, I said. Was just some, well, I don't even remember. This was just some simple example. It's not certainly not water, but it's a simple system. They just demonstrated in a Jupyter notebook how to calculate these cells.
Isotropic and isotropic.
I think it's only the isotropic one, and then it just shows the very spiky one. If you don't have a very long simulation, we smoothen it. So as I said, I hope to come to real example second parts, and I will review some of the results that we calculated recently. And there are lots of examples, but less examples of this function-based molecular dynamics derived from. But there's much more in the field of solid-state physics. So you can calculate phonons and then Raman intensities, and then you can calculate that. But because of this molecular dynamics, we need these hopefully 1 million time steps. It's much less common than just calculating the phonons. Any other questions at this point? Again, this is basically the same, except it's isotropic and anisotropic one as the infrared. Now I want to go to somewhat more exotic case. It has been used a lot recently, and this is now those 2 examples. They are linear spectroscopy, so linear absorption. Now we come to case where we shine two lights, two different frequencies, infrared, visible light, and then we look the signal, which is the sum of those two. This is some field of spectroscopies which have been developed in the last, they have become very popular in the last, let's say, 20 years. And in this class of families, there's also the second harmonic generation, so higher harmonic generations, these methods. In that case, second harmonic generation use two light signals which have the same frequency. Here one can vary those two. And this, and I will not go here to the derivation now. I would just mention that this signal in this subfrequency generation, there's no signal if the system is isotropic or if there's a central symmetry of the system. And this is, for example, liquid water. If you take bulk, you will have no signal because everything averages out. But if there are inhomogeneities, you can have those. I will take the case of vacuum liquids or vacuum liquid vapor interface. So when we have water in contact with vacuum, or there's some evaporation, so there's a low pressure of water. And this is one example, but these methods, they are used a lot also in solid cases to study interfaces, hidden interfaces, for example. So again, if you have two crystalline systems, both of them are centrosymmetric, so there is no signal from both. All the signal comes from this interface. The same is here. All the signal then comes from this interface. Nothing from, of course, from the vacuum, because there are only a few molecules from the vapor, water vapor, and the liquids, again, the signal vanishes there. So all the signal comes from this interface. And again, this can be used also in the case of solid liquid interfaces and so on. But this family of nonlinear spectroscopies. And just to mention how this is then calculated, basically we take the dipole moment and polarizability, then we form this correlation of these two. And I'm not going to any of the details, of course, this is a tensor and this is a vector. The dipole is a vector. But basically what we do is, now we don't take an autocorrelation function, but we take a correlation function of these two. And then we take the Fourier transform again, and in principle, we get the signal. Now this signal is much more noisy, and we would need longer simulations. So there are then tricks how to go about this. So the first simulations of this water liquid water interface were very noisy. They could do tens of picoseconds. So it's much more noisy, the signal, than in the case of infrared or Raman, because we have autocorrelation function. Now and then I will come to the solution. Yeah. So the signal comes basically only from the surface. I mean, very close to the surface.
This is more intensive thermal fluctuation.
Yeah.
Yeah.
And then I said the signal comes due to the inhomogeneities because liquid water, this is the interface, then there are lots of fluctuations. Then the question is how big cell you have to have these fluctuations at the interface and so on. But this is now in principle possible, but I will come to the solution how to treat the system and what people have done very recently. But this one I said it was some story more than 10 years ago that people calculate the signal, but it was very noisy. So this is I took from a recent article the result. So here's, I think this was this is the infrared that I already showed you. So this infrared spectrum of the water, this Raman. I think this is again the isotropic one. So you see the experimental one, simulated one in the liquid, and then the surface already. But sorry. But I will not discuss this now. What I want to show you is the result from this frequency generation. So you have these signals here. You have negative and positive signals. And what has been discussed the most and what's converged is the fastest, it's a function of the simulation time is of course the highest frequencies. Now the question is why is there a positive region, why is there a negative region? Now if you imagine what happens at the surface when you have the water molecules, at the interface you start to lose the hydrogen bonds, right? I mentioned initially you have the average two at donated hydrogen bonds to accepted hydrogen bonds. At the interface, you come to vacuum, so you cannot have all the hydrogen bonds in it. So what happens is, if you also, now this is light water, then this frequency is basically very close to the frequency of the free OH. And that's because what we see here is one of the, or at the interface, some of the water molecules. So this is the water molecule, the two hydrogens, the oxygen here. So one of the hydrogens points towards the vacuum. And so this OH is like a free oscillator. So this frequency is very close to the free OH stretching frequency. And then many of the other water molecules, they actually pointing the dipole down towards the bulk. But they have also disturbed the hydrogen bond network, and thus the signal is not zero. That's why there's this region slightly lower. These are the molecules which have a hydrogen bonds, but the hydrogen bond network is disturbed. So that's why there's the negative signal here. But that's just a very rough explanation what one sees in the spectrum. And this has been now
so that only for the layer consisted of molecules on the surface. It means just one molecular layer.
It's the real interface is actually much more rough than what we think that, okay, there's one. I mean, ice would be, yeah, there's in every, well, this hexagonal pattern, and, but the liquid water, there's a lots of discussion, also algorithms, how you define where is the interface, because there are water molecules which go up and they still go down and so on. So this real interface is really fluctuating a lot. It's not simple that one molecule turns away. So this is what I have learned. I mean, I have done the simulations. We have PhD students who have been working on this liquid weight interface. So it's really much more dynamic than also what I initially thought. And that's why also there's lots of molecules which are disturbed, not just one layer, but then what people have tried to do is they try to isolate the effect of the very first molecules which are highest, then the next ones and so on. They do kind of layer average signal in the simulations. So this is what is possible. This is kind of what state of the art. And I said that these methods were now they established this liquid water, I mean liquid vapor interface is basically not standard since years, but now people are, for example, putting the salt mixtures. Then they try to understand where the atoms, which is it cation, anion at the interface, and that's a function of the concentration and so on. So this is what was has been studied a lot, not pure water, but then molecules in water. So how they oriented and how did they affect the hydrogen bond network, and then that. So then two other issues I want to mention. The next one is I talked only about the total dipole moment of the system. Now, if you want to have a, let's say, more molecular picture, one way how to do that in calculations in these condensed systems is to use the so-called Vanier functions. I'm not going into the algorithm. The idea is just that the Korn-Sham orbitals that we get from VFT, they usually delocalized. They can be all over the system. Now we want something which is more localized around the molecules. And what we do is in these Vanier functions, what we usually use is the so-called maximally localized Vanier function. So it's a specific algorithm. Is that we take the Korn-Sham orbitals and then we make a mathematical unitary transform in the occupied space of the contram orbitals, and then we localize those. What we get is localized orbitals, which often have this chemical picture. In the case of liquid water, is this sp3. And this is an example just from one snapshot. So that if we have an oxygen, then let's take, I don't know if you can see, but for example, this molecule. So it has two so-called Wannier centers, which are along the OH bond, and then two, which are the kind of lone pairs on the opposite sides. And this is very close to the sp3. So the Wannier centers around the oxygen are two along the OH and two opposites. This is very close to sp3. But this is the method how to localize the contram orbitals. This has then been used. And then, for example, we can calculate the molecular dipole. So not the full dipole of the system, but we take the case of, for example, if you want to calculate the dipole moment, one of these water molecules, we take the positions of the ions, like we usually calculate the dipole, and then we consider the electrons, that we have two electrons at each of these Wannier centers. And people have shown that, okay, depending on the system, this gives pretty good approximation for the molecular dipole of liquid water. It's not fully well defined because the molecular dipole, there's always some overlap of the electrons along the hydrogen bonds. Small, but there is, and then the question is which algorithm is well suited. But what we use is the Wannier center. It's one of the methods, and then we can check the dipole moment at different hydrogen bond configurations, starting from the vacuum and isolate the molecule to the liquids, and then solidize. You can see these clear shifts of several dpi in the system. So this method, how we can localize this. Now, why I want to show this also is that now if I do battery, it's out more. I'm almost at the end. Very shortly, machine learning, because we will have more on this on Saturday. So the first issue was that we can learn the force field using machine learning. So that then we have these interactions. We don't need to solve the DFT equations or other Hartree-Fock or MP2 coupled plastic equations. We have the machine learned interaction potential, so force field using machine learning. This is what people do very standardized. So, and it has been shown in a couple of latest years that using the, for example, the Wannier functions or the Wannier centers, those were, if you shrink in the Wannier centers to the, or every Wannier function to its geometric center, that's the Wannier center, those which I showed in the example. So then we learn what is the molecular dipole if we have a certain neighborhood. So it's like learning the potentials, but now we learn not the forces on the system, the energy, but we learn the dipole. We have this and this neighborhood of a water molecule. What is the dipole? And the same we can do the polarizability. And what we do with this, then we take the molecular dynamics from machine learned molecular dynamics, and we calculate dipole for each molecule in the system as a function of the, or along the trajectory, and then we calculate the intensity. So we can do the infrared spectra if you have parameterized with machine learning the dipole. You have the parameterized polarizability, we can do Raman, and if we have both of them, we can do this some frequency generation. And this is now the solution how we get much cleaner SFP FH3 spectra, and we can compare with the experiments because we can do much longer simulations than using DFT. So we can do maybe nanoseconds. The noise in that signal is much lower than if we did DFT-based molecular dynamics. But this is kind of a way to feel this. I said this software that we can use to learn its potential. Often they now have also the option of learning also, let's say, vectorial quantities or tensorial quantities. quantities. So we can learn dipole Fourier speed and so on. Not only the forces, but beyond. And as said, with this, we can then simulate the infrared and the Raman much faster than the DFT-based molecular dynamics. So again, it's between the classical molecular dynamics in the speed, but now we have really a polarizable dipole. We didn't parameterize one dipole, the average, but we get in principle much better. So I don't know if I have 2 minutes. Can I just show very quickly? I mean, then if I can show the other file. I just show and then the kind of spectra that we have simulated. This is DFT based still, so it's very noisy. It was another file. The previous one. Okay. That erase it. Give them a full screen. All these. Well, in this paper, we then calculated, shown the temperature and coordination, so hydrogen bond coordination effects of Raman and infrared spectroscopies in liquid water. Again, this was a work, same. This is now experimental and simulated spectra. You see now. Well, this is, for example, the low frequency Raman spectra at different temperatures. It's very noisy. So this was DFT, 128 molecules, about 100 picosecond, 51 picosecond. Now with the machine learning, we could do this much faster. This is then, well, the infrared is a function of temperature. The dashed lines are the experiments at different temperatures. This is the shift towards higher frequencies because we have more and more molecules where the hydrogen bond network is broken. So we have more and more like free molecules. And then we consider the different hydrogen bond geometries. So how the frequencies shift when we have less and less hydrogen bonds. So this is the free OH, it's deuterium, so OD frequencies. And the full spectrum infrared, what was also shown quickly the other one. Now still change the regions. Just change the slide. So, and this was then using the machine learning, hitting those. All the curves are much smoother. The peaks are higher, narrower than here, because we could do only simulations and more molecules. And when here was the Raman. This was just to show the example we have done this. These are not published machine learning, but there are articles in the literature where you can find the same using machine learning. I said the article with a lot of them with the VFT based. There we are. Sorry for going over time.
I thank you very much. And now we are not in time, but probably we have some questions. So some questions during the lecture. What do you want with?
With machine learning, you can extend the time simulation to larger interval.
Yeah.
But do you see some new effects, or you filtered the noise simply?
Yes, mostly filtering the noise.
Yeah.
Because of course, we get better convergence at the low frequency spectrum because you need long simulations to have the low frequency. But qualitatively, it's the same.
I think you made the clustering how cluster organized.
Yeah, this is. I mean, this is the topic which is related to this, and this is what I gave a talk recently. It's about the collective dynamics. So our goal is to go to thousands, hundreds of thousands of molecules using machine learning potentials. We are going there, but it's not yet feasible.
Much for very interesting lecture. Actually, I'm at most experimentator, and in our biophysical department, we study non-covalent complexes.
Yeah.
By molecules with drugs or with biological active compounds and so on. And usually we, for explain experiments, for example, mass spectrometry, we are doing depth calculation of these complexes to realize structure, interaction forces, and so on.
Yeah.
And the main questions for us as a biophysicist, how it's, because it was a vacuum approach,
yeah.
How it can be related to real system, and we use PKM calculation to add water or some liquids.
Yeah.
Do you think that your DFT-based molecular dynamics can be used for non-covalent complexes calculation and describe properly the structures and interactions? Thank you.
I believe yes, but I take the middle way. So machine learning potentials, because with the DFT-based simulations, we are limited to, let's say, to 1,000 atoms.
The small one.
Yeah.
Small complexes.
Yeah. But with the machine learning, if we can parameterize the force fields, now there are so-called foundation models, which one doesn't need to fit. So it's kind of a general potential, like just taking from a catalog element and the potential. So this has become available. And with this, it's easy to do nanoseconds and so on of thousands of atoms.
But
it's feasible.
It's still a long machine.
Well, this foundation, then for the intensities, this one has to learn. So now there are these potentials which are meant to be generic, and one doesn't need to feed it anymore. And these are the so-called foundational models. They are not very accurate yet. So some people take them and then they improve the potential a little bit. So they take the standard one from the library and then they improve it a bit for their system. But this is coming at the talks last week, but people are saying that they are improving all the time, the accuracy of these. Then you can just pull it from the library. But still you don't have the intensities because they are only a potential for the interaction, not for the signal, but then you can do, at least the power spectrum easily. And I guess then if you have model dipole moments, then you can do also the infrared Raman.
The colleagues like